All right, so we want to take a look at finding centroids of regions or centers of mass or center of gravity, whatever you want to call it. The region I'm going to look at to start with is something along the lines of this simple region. I call it type 1 region. Anyway, it's bounded above by a curve y equals f of x, bounded below by the curve y equals g of x, bounded on the left by x equals a, and on the right by x equals b. Okay? And we want to find essentially the balance point. There's some spot in the middle where you could stand it on the head of a pin and it would balance. Well, to find that, we're going to first of all find the x-coordinate, which is going to be called x bar, or average x value. That bar over a variable in statistics quite often means the average value for that variable. So we want to find the average x value, and we want to find also the average y value. And we'll do this one at a time. So the way we do it is we essentially think of this region as cut up into a bunch of pieces. Imagine that. So we've got a bunch of little rectangles here. For every value of x, for each value of x between a and b, you've got one of these rectangles. And I'm thinking of where does this balance along the x-axis. So I'm going to do it very much like I did in the last video, where I'm going to take each one of these things, consider as a weight sitting on the x-axis. I'm going to take that weight times the distance away from the y-axis. That's, I think of my fulcrum as being right here. So I take the weight times the distance away, and I'm going to add them all up. That will give me what's called the total moment in that direction. And this is a moment away from the y-axis. So this is actually described as, the notation is m sub y. And so they think about each weight times the distance. Well, the distance for each x value here, the distance from the y-axis is whatever the x value is. So this is x times, and now I need to come up with a weight, okay, or a mass. And what we do is we essentially say, well, what's the area? Well, the area is the top. So the area is the length times the width here. So the width is a little dx. And the length is the y value at the top minus the y value at the bottom. So f of x minus g of x. Now that's actually just the area. It's not the weight. And so we then often multiply by the density. I'm going to just use, that's a Greek letter, delta equals density. Now, it's going to turn out that I don't need the density in most of these examples because we assume uniform density, and it's going to cancel out, as you'll see in a moment. But sometimes density might be a function of x, right? So it might be like thicker in some places and thinner in other places. But it has to be, at least for the point of view of what we're doing this quarter, it has to be, delta can be at most a function of x. When we get to calculus 3, and we're doing double integrals, then we come back to this and say, well, density might change anyhow, and you have to take that into account. But anyway, m sub y is the moment, the total moment away from the y-axis. Now, there's one thing I didn't do yet, because I didn't add them all up. For each value of x, this is the moment for that particular weight. This weight sits on the axis right here. Then I got to go do it again for this rectangle over there. It sits right there. So it'll be a different value of x and maybe a different area, because the difference between the top and the bottom might be different. So what I now need to do is I need to add all of those up, each one of those little moments, all the way from x equals a to x equals b. Remember, to calculate the center of gravity, what we did before was we added up all these moments, and then we divided by the total weight, or the total mass. Well, the total weight, or the mass, whatever you want, is, let's just say mass, is going to be the area of each piece, so f of x minus g of x times dx, that would be the area of each rectangle, and multiply that by the density, and then integrate that from a to b. If I didn't have the delta, I'd just be calculating the area, but delta is the density, so that changes the area into a mass or a weight, depending on whether it's mass density or weight density. And now I've got total moment, total mass, and so the x bar, the average x value, is going to be my over the mass, which is the integral from a to b, delta x, delta times x times f of x minus g of x dx divided by the integral from a to b of delta times f of x minus g of x dx. Now, in some examples that you'll see as you work through the problems in the book, some of the examples have delta being a function of x, in which case, whatever that function is, you're going to multiply it in here in order to do the integral. On the other hand, if delta is a constant, it factors out. Right? The delta comes out of the integral here, comes out of the integral there, and then it cancels out. And in fact, you don't even need the delta in the event. If delta equals a constant, then x bar looks like this. X bar is just the integral from a to b of x, f of x minus g of x, get that parentheses, dx, divided by the area, the integral from a to b of f of x minus g of x dx. Okay. If the density is constant, which in many of the examples it is. Right? If you're just taking, and to me this is the geometric version of it, this is what I would call the centroid. When I'm looking for sort of the balance point of this region, and I just think of it as, the book uses the word a lamina. A lamina is a very thin layer, and if it's uniformly dense, just consider the area as being the weight, and find that center point. That's what I would call the centroid. Right? If there's non-uniform density, then it's more like a center of weight or a center of mass, where it might be skewed to one side just because you got a lot of weight over here, maybe not so much over there. Anyway, one thing I want to point out, and this always bugs me, is that to calculate x bar, you use my. It just seems like you should call it mx because you're calculating x coordinate of the center of mass. But it's the moment away from the y-axis, and if you're measuring distances away from the y-axis, you're measuring x values. Okay, so it's my over the mass, or in the case of constant density, it's my over the area. Now, to calculate y bar, why is this thing giving me, there we go. Now, for y bar. Same picture, all right, we're still dealing with the same region. So I've got my y equals f of x on the top. I got my y equals g of x on the bottom. Still from a to b. I'm still, for each value of x, I'm looking at one of these rectangles. But now instead of thinking of that rectangle as sitting on the x-axis, I got to think of it as sitting on the y-axis, right? Because I'm going to be measuring distances away from the x-axis. I'm thinking of my fulcrum sitting here now, and trying to tip back and forth, this way. So all of this weight is sitting on the y-axis. Well, I mean, I look at that weight, and it's sitting from here to there. And each rectangle spreads out over that y-axis. And I want to consider just one particular place that it sits. Well, the particular place that it sits, the most reasonable thing to say would be in the middle. So take that rectangle, find where the middle is, and say that's where this weight is sitting on the y-axis, that y value. Right? For another rectangle, right, for this rectangle over here, you find its middle's down here, and you say, okay, well that middle is sitting right there on the y-axis. So each one of these rectangles, we're going to say how much weight is there times this distance away from the x-axis. So you're measuring the y value up to that center point of the rectangle. Okay. Well, first of all, how do you find the center point of the rectangle? Y center here. Well, it should be the average between the top and the bottom, right? So it's f of x plus g of x divided by 2. I mean, how do you take the average of a couple things? Add them up, divide by 2. So top, bottom, the average value is the middle. And that's going to be what we use for our arm, for the distance away from the fulcrum, the y value getting up to there. So now, what we're going to call mx, or the moment away from the x-axis, is going to be, well, this distance, f of x plus g of x divided by 2, times however much weight or mass or whatever is right there. Well, that would be, the area is f of x minus g of x. The width is dx. And if you have a density function, then you would multiply by the density as well. And you do that for every one of the rectangles for x values between a and b. So there's all these rectangles for every single value of x. You've got one of these rectangles. And so you're going to add those all up all the way from a to b. The total mass is the same as it was when we were calculating x bar, so I don't have to write that down again. So the average y value now is mx divided by the mass. Go away. Sometimes this thing does weird things to me. It's beeping and bubbling, and there we go. Here we go. So this would be the integral from a to b of the density times f of x plus g of x divided by 2 times f of x minus g of x dx. Let's put that in parentheses. And all divided by the mass, which is the integral from a to b of the density function times the area. So f of x minus g of x dx. Again, in the case where you have constant density, you can cancel out the deltas because they factor out and cancel. So if delta equals a constant, then you're just looking at this thing right here is equal to the integral from a to b of, I'm going to continue to write it this way. I'll show you a shorthand way of writing it in a moment, but I don't like the shorthand way of writing it because it doesn't lead me to the formula. And I hate memorizing things. Okay. When I think about calculating center of mass, I think about moment divided by mass. Total moment divided by total mass. Moment is always a distance away from a fulcrum times a weight. When you look in the book and you see the formula for y bar, they probably don't have this. They have what looks a bit simpler. And here's what happens here. If I take that 1/2 out, let's say 1/2 the integral, then you got f of x plus g of x times f of x minus g of x. Well, when I FOIL that out, that's really nice because I've got the f of x times f of x, that's f squared of x. I've got the f of x times negative g of x, and I've got f of x times positive g of x. The outside terms and the inside terms cancel out, and then you've got the minus g squared because you've got the g of x times minus g of x. So this looks like this. So they will, maybe they'll write it that way. Maybe they'll write it this way, f of x squared minus g of x squared, right, from a to b over the area, a to b, f of x minus g of x dx. This to me does not look like the calculation of moment. I don't see a distance times a weight. I see outside radius squared minus inside radius squared. It's like, what? We're not rotating anything here.